In section 8, we will introduce the Z transform, a Laplace transform specialized to discrete time signals. This Z transform will be used to solve difference equations and to analyze discrete time, linear time invariant systems. It can be used to describe a system using a transfer function, and this transfer function can be used to study stability in the Z domain. Well, before starting this section 8 on the Z transform, we'll talk about the geometrical series, and we're more in particular interested in this sum. It's a sum where k ranges from k0 to k1 of q to the power k, and what we intend to show is that this sum is equal to this quantity over here. So what we'll do is do a so-called proof by induction. So we'll see that this property is true for k1 is equal to k0, right? Then we'll assume that this sum is correct and that the property holds for k1 is equal to k, right? And we'll show, if this is true, that it is also true for k1 is equal to k plus 1. Since the property holds for k1 is equal to k0, it will hold for any k from k0 to k1. This is a proof by induction. It is easily proved that the property holds for k1 is equal to k0. So let us write as k0, k0. It's a sum where k ranges from k0 to k0. So there is only one element in the sum. Okay, so it should be, of course, and this is the question, q to the power k0, and we see that this expression here, when k1 is equal to k0, is q to the power k0 minus q to the power k0 plus 1 minus, over 1 minus q. This can be rewritten as k to the power k0 times 1 minus q over 1 minus q. Okay, so this can be simplified, and we see that indeed the property is verified when k1 is equal to k0. Well, the second step is now to show that if the property holds for k1 is equal to k, it also holds for k1 is equal to k plus 1, right? So what we'll do is take the sum up to k1 is equal to k. There we know that the formula is verified, and you've got it over here. And then we'll add an additional term, since we want to show that the formula holds for k1 is equal to k plus 1. So the additional term is the q with the power k plus 1. So what we'll do is bring everything to the same denominator, right? So these are the terms that are coming from here, and if we put everything under the same denominator, we'll have, well, this is q to the power k plus 1 times 1 minus q. Okay, so q to the power k plus 1 minus q to the power k plus 2. These two will compensate each other, and we are left with this formula over here. And this shows that this formula, if it holds for k1 is equal to k, well, it holds also for k1 is equal to k plus 1, and therefore for all k1. So we have shown that this property holds. Well, of course, you should not be able to do this prove by induction at the time of the exam, and later on in the course we'll use this formula with k0 is equal to 0, and in this case what will happen is, of course, you will have a 0 over here, and this here will be replaced by a 1. So here's this formula with k0 is equal to 0. Of course, we assume here that k1 is larger than 0, and this is what we obtain. And in this course we'll assume that k1 tends to infinity. So what we'll look for is a sum where k ranges from 0 to infinity of q to the power k, right? Well, if you let k1 tend to infinity, well, if q in modulus is larger than 1, this is not going to converge. This is only going to converge when k1 tends to infinity if the modulus of q is smaller than 1. Okay, if the modulus of q is smaller than 1, if you take powers and let these powers go to infinity, of course you'll have a term that goes to 0. So under this assumption here, and with k1 tending to infinity, this term is going to disappear. Okay, so this is very important, and this is one of the things that you should know for this section 8 on the Z transform. You can also see here that if q is smaller than 1 in modulus, but it approaches 1, well, you'll have a sum that will become large, because you'll have here at the denominator something that will be very small. Don't forget that this formula and this assumption, they go together. So at the time of the exam, if you put this equation on your sheet of paper, well, you should also put the assumption with it. Okay, if the assumption is not there, this formula is meaningless. Well, in order to introduce the Z transform, we'll go back to a sampled signal, and we take the Laplace transform of that sampled signal, and we'll obtain the so-called Z transform. So remember that a signal is sampled by multiplying the signal that you want to sample by the Dirac-Combes. So if we write that down, it's f of t sum k going from minus infinity to infinity of a bunch of deltas that are shifted by kts. This can go into the sum, and we obtain k is equal to minus infinity f of t delta t minus kts, right? And now we are ready to apply the shifting property. Notice here that the delta is located in kts, so you can replace f of t by f of kts, and so this is how you obtain this sampled signal. Well, this sampled signal fs of t is a continuous time signal, so we can take its Laplace transform over here. So we can write the Laplace transform of a sum over k of f of kts delta t minus kts. We know that this Laplace transform is linear, so this is how we go from here to here. And then, well, I won't do it, but you should be able to find that the Laplace transform of a delta is equal to 1. Now you can start from the definition of the Laplace transform, and you should also be able to show that if you have the Laplace transform of f of t, and it is f of s. Then if you do the time shifting of the function f of t by a quantity tau, well, the Laplace transform will be e to the minus tau s f of s. So this means that this Laplace transform is, this will play the role of tau over here, is e to the minus kts s, right? So this is how we arrive at this expression over here, and we just want to take this e to the power tss with us and to drag it with us. So what we'll do is define a variable z that is the exponential of tss, and if we do this, we can rewrite the expression here as a sum over k. Remember that k is ranging from minus infinity to infinity. Instead of writing explicitly the dependence on ts, we'll use this kind of short notation f of k, and we'll write this one here using the z that we have defined. So this will give us z minus k, and this will be the z transform of the sequence f of k. Okay, and you can simply obtain it by looking at the Laplace transform of a sampled signal and then define the variable z as follows. So this is something that you should be able to obtain by going through this kind of calculations. So if we are given a discrete time signal f of k, right, we can compute its two-sided z transform using the definition that we have shown here in the previous slide. Okay, this transform is associated with a region of convergence, and the region of convergence is the region where this sum over here will converge. Remember that in the Laplace transform we also had this two-sided Laplace transform, and it was not very useful in solving differential equations with initial conditions. And anyway, what we are doing is, well, considering causal systems, causal signals. So in the same way, this two-sided z transform will not be very useful, and it is therefore necessary to define a one-sided z transform. For the one-sided z transform, we assume that f of k is either causal or that it is made causal by multiplication with a unit step. So the contributions for k negative are all 0, and we can start the sum at k is equal to 0. Again, there will be an associated region of convergence. So what we do now is obtain the region of convergence of the one-sided z transform of the discrete time causal signal f of k. So it's denoted like this, and what we want to obtain is the region of convergence. Before we start, remember that z is equal to the exponential of tss, and remember that s is equal to sigma plus j omega. So you can write z as the exponential of ts times sigma plus j omega. It's just putting the expression of s in the expression of z, and this one you can rewrite as e of ts sigma times the exponential of j omega ts. This is a real number and we'll call it r. and we'll define here a discrete frequency so that we can write z in under the following form. So it's a polar form. Okay, so this is what is given over here with a link between r and this capital omega and the sigma and the omega from the Laplace transform. Okay, so let us now come back to this region of convergence. We want to find the z's for which this sum is converging. So what we'll do is take the absolute value and remember this triangle inequality that we've used now for the fourth time. So the absolute value of a sum of ai is smaller or equal to the sum of the absolute values of the ai, right? So if we use this, we can obtain an upper bound of this, and here it is. And this one here, it's living on the unit circle, so its modulus is 1. So this is how you go from here to here. And you see that if this sum is bounded, then you have a sufficient condition for this z transform to be defined. Okay, again, we prove sufficiency. You can prove there is also necessity, but it's much more complicated. So we see here that if this sum converges, then the z transform is defined, and this sum converges if this sequence here is absolutely summable. And this is often the case if you choose r large enough. You can see that if you choose r large enough, well, this is going to be absolutely summable. The values of r for which the integral converge define the region of convergence. Notice again, as in the Laplace domain, that this condition does not depend on the discrete frequency capital omega, just as for the Laplace transform, where the region of convergence is independent of the frequency omega. So the region of convergence is the set of z that can be rewritten like this, as we have shown over here, such that this sum converges. So let's have a look at the region of convergence of the Laplace transform of a function f of t. It was the set of s is equal to sigma plus j omega, such that the following integral, and we'll again use also the one-sided Laplace transform, f of t e to the minus sigma t dt converges. This looks a lot what you have got over here, and if you take t is equal to kts and you plug this in here, you will see that you have a sum of k is going to from 0 to infinity of f of k e to the minus sigma k ds, right? And this here, since r is equal to e to the ts sigma, this is indeed what you have over here. So there is a similarity between the region of convergence in the Laplace domain and the region of convergence in the z domain. This is kind of logical because you can see the Z transform as a Laplace transform of a sampled signal. You will see that everything that follows hinges on the geometrical series. Okay, so this is this sum over here that is equal to 1 over 1 minus q. Remember that this formula is only valid under the assumption that the modulus of q is smaller than 1. Then there is the one-sided Z transform. This is something that you should be able to obtain from the Laplace transform of a sample signal. And remember that once you write this Z transform at some stage, you say that Z is written as the exponential of TSS. So there is a relation between the Z variable and the S variable. And what we could add here is also the region of convergence of the Z transform of the sequence f of k, and this is the set of all z's that you can write under polar form r e to the j omega, such that the following sum that ranges from 0 to infinity of f of k r, not z, r minus k in absolute value converges. So in other words, the region of conversion of the Z transform of the sequence f of k is the set of all z's such that this sequence here is absolutely summable. We can define the concept of a pole and a zero in a similar fashion than in the Laplace domain. So we are given a sequence f of k, and if we take the Z transform, we'll obtain a rational function in Z. This means that f of z can be written as nz, the numerator polynomial, divided by dz, the denominator polynomial. And a zero of f of z is a value of z for which f of z is equal to 0. So obviously it's a value of z for which nz is going to be 0. A pole of f of z is a value for which f of z tends to infinity. That is a value of z for which the denominator polynomial is 0. The poles and zeros of f of z can be complex, but if they are complex, they are going to be complex conjugate pairs, because we assume here that nz and dz are polynomials with real coefficients. And of course there can be no poles in the region of convergence. Remember that the region of convergence is the z for which, well, the sum that is used to compute f of z convergence, and obviously a z where you have a pole is a z where f of z does not converge, so no poles are included in the region of convergence. What we will do is again focus on causal sequences f of k, and we can consider two cases: causal signals of finite support and causal signals of infinite support. And what we'll do is we'll have a look at the region of convergence of the Z transform of those signals. So let's start with causal signals of finite support, and the support is the interval k0, k1, which means that f of k is 0 outside this interval. Since we're considering causal signals, k0 of course is larger or equal to 0, and we'll assume of course also that k1 is going to be larger or equal to k0. So if k0 and k1 meet this condition, there is no reason to expect problems in the convergence of this sum, since you have a finite amount of terms, right? So the region of convergence will cover the whole S-plane, but in most cases we'll have to exclude z is equal to 0 from the region of convergence. So the easiest thing is to take an example. So this is k here, and this is f of k, and here is my signal, so it's causal. Okay, and so for instance, like take a signal that looks like this, and then 0 for subsequent case. Okay, so here we have k0 is equal to 0, and we have k1 is equal to 2, right? This is the support of the signal f of k. And if we have a look at the z transform, what will happen here, since we have only 3 terms, it will be f of 0 z0 plus f1 z minus 1 plus f of 2 z minus 2, and all the other terms are 0. Okay, so if we assume this is a 1 here, and we have a 2 over here, this is going to be 1 plus 2z minus 1 plus z minus 2. Okay, so this is the z transform of my sequence f of k. So we'll see quite a few z transforms of sequences, okay, so that we have again this catalog of z transform. But the easiest thing with a causal signal of finite support is to simply use the definition, and you easily obtain the z transform of the sequence. And you can see here indeed that because of this z minus 1 and this z minus 2, we have to exclude z equal to 0 from the region of convergence. So it will be the whole z plane minus z is equal to 0. Well, let us now look at the region of convergence of a causal signal of infinite support. And the first thing that we can do is have a look at the definition of the region of convergence that we had obtained previously. Okay, so it was a set of all z that could be written under polar form r e to the j omega, such that, well, this sum ranging from 0 to infinity of f of k r minus k in absolute value is converging. Okay, so it's all z such that this sum converges, so all z such that this sequence is absolutely summable. And this you can rewrite as f of k divided by rk, right? And you can kind of see that if you choose r large enough at some stage, well, this sum will be convergent. So we can kind of view that this is the z plane, that, well, the domain of convergence or the region of convergence will be the outside of some circle, right? You can see here that if the radius becomes large enough, this sum will start to converge. So this is one way to see things. Another way is to remember how we find the region of convergence in the S plane. So this the S plane, so this is sigma, this is J omega, and remember that in the Laplace domain the idea was to look at all the poles. You remember that there should be no pole in the region of convergence. We had also seen that the region of convergence was to the right of the pole or poles with maximum real value. Okay, so this was the region of convergence in the S domain. Remember that this is sigma is equal to sigma max. Okay, so sigma max is coming from the pole with maximum real parts. So now what we can do is remember that Z is equal to R e to the j omega, and that R is e to the ts sigma. So this vertical line here that corresponds to sigma is equal to sigma max will be transformed in an R max. Okay, so it will be a fixed radius. Okay, so a vertical line in the S-plane will become a circle in the Z-plane. So what we can do is do something similar, and this will now be the Z-plane. We can have a look at all the poles, and for instance this have 3 poles, 2 complex conjugate poles and a real poles, and then you have a look at the pole with the largest radius, and there are 2 over here because they are complex conjugate. So this will be R max, and then the region of convergence will be constructed on this pole with the largest radius. It will be outside a circle of a radius R max. So this is the region of convergence in the case of a causal signal with infinite support. So you take the pole with the largest radius, and this radius is R max, and the region of convergence is outside a circle of radius R max. As you have noticed, I've skipped quite a few slides. These slides will talk about the Z transform of non-causal signals and a link between the one-sided Z transform and the two-sided Z transform. These slides are there for your information only, so if you're interested you can have a look. Obviously they will not be the topic of the exam. The S domain and the Z domain are linked by the relation Z is equal to the exponential of Ts times S. And if you look at this connection and replace S by sigma plus j omega, you can rewrite Z as follows, and this will be R, and this can be rewritten as the exponential of j omega, right? So we've kind of gone from a variable S expressed as a complex number but in Cartesian form to a Z that is expressed in polar coordinates. So R will be the radius, and you can see here that R will be positive, and it will be, well, in between 0 and infinity. The angle here, capital omega, is the discrete frequency. It's linked to the frequency in the Laplace domain, that is in radians per second. So you can see that you have radians per second times second, so the discrete frequency will be expressed in radians. Observe also that the variable r is only linked to the damping factor sigma. The relation between the s plane and the z plane is obtained from this relation. If you plug in s is equal to sigma plus j omega in here, we have seen that you can write z as r exponential of j omega. So it's a complex variable in polar form, where r is the radius and it's defined like so. It depends on the sampling period and on the damping coefficient sigma, and the discrete frequency omega is linked to the analog frequency omega times ts. So omega has units radians per second. This means that the discrete frequency will have units radians per second times second. See also here that r is equal to the modulus of z, and that omega is equal to the argument of z. We'll now have a look at the radius r, or the modulus of z, as a function of sigma, the damping parameter in the s domain. You can see that when sigma is negative, you'll have the exponential of a negative number, so the radius, the modulus, will be smaller than 1. If you plug in sigma is equal to 0 over here, you'll have the exponential of 0, which is 1. So sigma is equal to 0 will correspond to a radius of 1 and a modulus of 1. So you can kind of see that the j omega axis is mapped onto the unit circle. Modulus of z is equal to 1. If you plug in a positive value over here, the exponential, so the radius, will be larger than 1. What we'll do now is look at the link between the discrete frequencies and the analog frequencies, and we therefore have to consider this relation over here. This is the discrete frequency, and here we have the analog frequency. Remember that z is r exponential of j omega, and the discrete frequency omega is also the argument of z, right? So what we want to do here is consider the entire z-plane. So we can do this by considering a discrete frequency, or the argument of z, in between minus pi and pi, and taking the radius positive or 0. So in this way we have selected the whole z-plane. Let us now look at the equivalent analog frequencies, and by looking at this equation you can see that if you take this interval and you divide by ts, you obtain the equivalent interval for the analog frequencies. So omega ranges from minus pi over ts to pi over ts. So it ranges from minus the Nyquist frequency to the Nyquist frequency. So you can see here that in the S domain we have kind of a central strip here of width 2 pi over ts, and this central strip is mapped on the entire z-plane. What we can do right now is consider an equivalent interval that is given over here, that is shifted by 2k pi, where k is an integer. Okay, and you can kind of see that this interval is equivalent to the interval that we have considered before, in the sense that we'll again generate the whole complete z-plane. If we now look at the equivalent analog frequencies, and looking at this equation, we have to divide by Ts, and we find the interval, the corresponding interval for the analog frequencies. And you can see that at least when k is different from 0, we'll define strips of width 2 pi over Ts that will be different to the strip that we had already considered before. Okay, so you can kind of see here that the S domain is decomposed in strips of width 2 pi over Ts, and that each of these strips is mapped on the entire z-plane. We have seen in the previous slide that strips of width 2 pi over Ts that cover the left and right half planes of the Laplace domain are mapped into the entirety of the z-plane. The width of such strips is of course related to the Nyquist condition. This condition says that when you sample analog signals, the frequency content should not go above the maximum frequency omega n, which is the Nyquist frequency, pi over Ts, where Ts is of course the sampling period. When the sample period tends to 0, the width of the strip will tend to infinity, and in the limit this central strip will cover the whole left and right half planes of the Laplace domain. Let us look at this in a visual way. Remember that the relation between the z domain and the s domain is given by this relation. If you plug in s is equal to sigma plus j omega, you should know by now that you can find that z can be written as a complex number under polar form, where r is the exponential of Ts sigma, and where the discrete frequency omega is related to the analog frequency omega by this relation over here. So what we'll do is first do what we've done in the previous slide and look at things more visually. So what we'll do is select this discrete frequency in the interval pi minus pi or minus pi pi, and we'll consider in general that r is positive or 0. So if we have a look at the corresponding analog frequencies, we have to divide by Ts, so we see that omega, the analog frequency, is in between minus pi over Ts and pi over Ts, right? And if you look at it in the S-plane, well, you can see this as a strip. This is this central strip of width, well, the width here is 2 pi over Ts, right? So the entirety of this strip of width 2 pi over Ts is mapped to the entirety of the z-plane. So what we'll do right now is, and this is what you see here in gray, look at this half strip of width 2 pi over Ts, and we'll first have a look at the half strip that corresponds to sigma smaller than 0. Well, if sigma is smaller than 0, you can see from this relation over here that this will be corresponding to r smaller than 1. And this is what is here indicated in gray. This half strip to the left of the j omega axis is mapped to the inside of the unit circle. So now we can also have a look at what happens, and I'll change color here. When sigma is larger than 0, well, you can see from the same relation that this will correspond to r larger than 1. So this strip, this half strip to the right of the j omega axis will be mapped to the region that is outside the circle. Modulus of z is equal to 1, right? And what we can do now is have a look at what happens when sigma is equal to 0, and sigma is equal to 0 is that part of the half strip that is on the j omega axis. And if you start from this point over here, that corresponds to a analog frequency of minus pi over ts, you start over here at minus pi, right? And you go from here to here. What you will do is travel on the unit circle until you've reached a discrete frequency of pi, okay? And you go from C to B on the unit circle. So what we can do now is take another interval for the discrete frequency. Let us take an interval pi, 3 pi, and remember that the discrete frequency is the analog frequency times ts. We'll choose here again r is larger or equal to 0, so this corresponds to any value of sigma. Remember that r is exponential of ts sigma, so this corresponds to negative and positive values of sigma. And you see that this radius, of course, is always positive or 0. So what are the equivalent analog frequencies? You have to take this relation and divide by ts, and you see that the analog frequencies are in the range pi over ts and 3 pi over ts, and we consider all values of sigma. Okay, so we can kind of see that we consider strips where the analog frequencies are in between pi over ts and 3 pi over ts, and see that this is a different strip than the one that we had considered in the previous slide, but it's also a strip of width 2 pi over ts, and this whole strip, okay, left part and right part, is mapped on the entire z-plane. So if we consider sigma smaller than 0, if we look at this relation over here, we see that r is going to be smaller than 1. So the half strip to the left of the j omega axis is going to be mapped inside the unit circle, and this is what is shown here in gray. We can again have a look at what's happening when sigma is larger than 0. Obviously we'll have r larger than 1, so this half strip to the right of the j omega axis will be mapped to the region outside the unit circle. And again, what we can do is look at what's happening on the j omega axis. Remember that we're considering frequencies that range from pi over ts up to 3 pi over ts. So what's happening is that we're moving on the j omega axis as is shown over here, and that the corresponding discrete frequencies will range from pi to 3 pi. So we start over here with a discrete frequency of pi, and then we move, and so this corresponds to the point C, by the way, and then we move on the unit circle, and here we have moved to 2 pi. Okay, so this corresponds to this point over here, and if we continue, well, we'll end up in a discrete frequency 3 pi, and this corresponds to the point B, but in the z domain, B and C, they correspond and they are the same value z. So I think that you understand things by now. So here we have another interval for the analog frequency. You go from minus 3 pi over ts up to minus pi over ts. So this corresponds to discrete frequencies from minus 3 pi up to minus pi, and here we have sigma smaller than 0, since we have r is equal to e ts sigma, so this will correspond to the region r is smaller than 1. So again, this left half strip, left of the j omega axis, will be mapped inside the unit circle. So here we consider analog frequencies, and this is this central strip in between minus pi over ts, pi over ts. So the discrete frequency will range in between minus pi and pi, and here we consider sigma larger than 0. Remember that r is e to the ts sigma, so this will correspond to r larger than 1. So this central strip, and we have seen this previously, to the right of the j omega axis is moved to the region outside the unit circle. We have seen that all these half strips to the left of the j omega axis are all mapped to the inside of the unit circle. We have also seen that portions of the j omega axis, here going from minus pi over ts to pi over ts, well, this portion of the j omega axis is mapped on the unit circle. You have to take the discrete variable and go from minus pi to pi. This is also the case for this portion of the j omega axis. It goes from a frequency, an analog frequency of pi over ts to the frequency 3 pi over ts, and again it is mapped on the unit circle. The discrete variable comes from pi to 3 pi, and I guess you can start to understand now. We have that this portion that corresponds to the analog frequency minus 3 pi over ts to minus pi over ts, well, it's also mapped on the unit circle. The discrete frequency goes from minus 3 pi to minus pi. We can now make the link with the sampling theorem of section 6. Well, if we're going to consider spectra of signal, we need to compute the Fourier transform of a signal f of t. This is f of j omega. And remember that if sigma is in the domain of convergence of the Laplace transform f of s, we can simply use the Laplace transform and replace s by j omega. But what is important is that we have to work on the j omega axis to consider spectra. The Nyquist frequency says that the signals that we are going to consider must be band limited. This means that they have, well, support in between minus pi over ts, pi over ts, and minus pi over ts is minus the Nyquist frequency, and this is the Nyquist frequency. So why do we need this condition? Well, we have just seen that these different portions here, you have here j3 pi over ts minus j3 pi over ts. These different portions over here of the j omega axis, they will all be mapped on the unit circle. So if this condition is not met, these different portions are going to overlap after sampling in the z domain, and this is going to cause aliasing or frequency folding. So we need this Nyquist condition. So what will happen after mapping to the z-plane? Well, this spectrum on the j omega axis and this, well, region of interest over here will be mapped to the modulus of z is equal to r is equal to 1, and this analog frequency in this range will be mapped to the discrete frequency in between minus pi and pi. And if we meet the Nyquist condition and this signal f of t is band limited, then when we'll go around the unit circle in the z-plane here, the mapped frequency response, the mapped spectrum, will repeat itself periodically, and this is precisely what we had seen about the spectrum of the sampled signal in section 6.